We're going to go ahead and get some more perspective on multiple regression, and we can begin by contrasting it with bivariate regression as is presented here. So this is what you may remember from high school is a Venn diagram. We have two variables, a predictor x and a dependent variable y. The correlation between x and y is 0.50. What is the percentage of y that is explained by x? And what I mean to say, what is the percentage of variance? And in this situation, x is explaining 25% of the variance in y. To get that 25%, we square r. So r squared, 0.50 squared is 0.25, and multiplying by 100, we get 25% of the variance in y is explained by x. Now, the circle for x conveys the variance in x. The circle in y for y conveys the variance for y. The overlap between the two circles conveys the percentage of variance in y that is explained by x. So the overlap here is 25%. Now here we have a multiple regression situation. We have two predictors, x and q. Now, x explains 25% of the variance in y. There's the overlap. Q explains 25% of the variance in y. Now, in this situation, x and q are uncorrelated. So the x and q are uncorrelated. Therefore, the circle for x and the circle for q don't overlap. Now, what is the explained variance in y in this situation? X explains 25% of the variance. Q explains 25% of the variance. So in this situation, 50% of the variance in y is explained. Now, I forgot to mention in the prior slide, 75% of the variance in y was unexplained. So here's a quick glance backwards. Here you are seeing the 75% of the variance in y that is unexplained by x. Back again, and here the unexplained variance is 50%. Now note in this situation, because x and q are uncorrelated, or more explicitly, because their correlation is 0, the variance that x explains in y does not overlap with the variance that q explains in y. And that's why we can simply sum 25% and 25% to get 50%. Now, whenever you're explaining variance, the unexplained variance is getting smaller. The unexplained variance is much the same thing as your sampling error. So as you explain more and more variance, your sampling error is getting smaller. And we had an analogy earlier to the haystack. So as you explain more and more variance, your haystack is getting smaller. So in this situation, if you were you're wanting to detect the effect of x on y, say, well, you're going to have more power to do so in this multivariate setting, and that's because there is less unexplained variance. So I will quickly mention that the prior video showed you that multiple regression controls for other predictors, and by so doing reduces bias from them. But another advantage that can often come from multiple regression is making the unexplained variance smaller, and therefore an increase in statistical power can often come from multiple regression. Now we'll want to offer some caveats on that, and you'll see them as we keep going. Now, in the prior slide, X and Q were uncorrelated, and that was conveyed by the absence of overlap between their circles. Now, in a pragmatic sense, it is rare in multiple regression for two predictors to be uncorrelated. Often there is correlation. That correlation can be either weak or strong. In this Venn diagram, taken individually, X and Q each explain 25% of the variance in Y. So in other words, if we look at X, apart from Q, explains 20% of the variance in Y, but then it explains an additional 5% of variance in Y. This 5% of variance in Y that it explains overlaps with the variance that Q explains. So in sum, X explains 25% of the variance. And it's the same question, same result for Q. 20% of the variance in Y is explained uniquely by Q, and then an additional 5% of the variance that Q explains overlaps with, that is the same as variance that is explained by Y. Taken together, how much of the variance in Y X and Q explain? They each explain 25%, but 5% of that explained variance is jointly explained. So taken together, X and Q explain 45% of the variance in Y. What is the unexplained variance? The variance in Y that is not explained by X and Q. We need to subtract the 45% of the variance that is explained from 100%, and you see that 55% of the variance in Y is unexplained. And I do note that there was a typo, and that was fixed here, so that this now is indeed correct. Let's compare this situation here to the bivariate situation. In the bivariate situation, recall that 75% of the variance in Y was unexplained. Here, only 55% of that variance is unexplained. So if we're wanting to detect the effect of X on Y, the fact that the unexplained variance has decreased, in other words, the haystack's gotten smaller, this has the effect of increasing the power of a significance test to detect the effect of X on Y. Yet, in this diagram, X and Y are correlated. Now, to the degree that two predictors are correlated, it actually becomes more difficult to detect their unique effect on a dependent variable. So the fact that X and Q are correlated here, as contrasted to a situation as shown in the prior Venn diagram where X and Q were uncorrelated, the fact of correlation decreases the power of a statistical test to detect the unique effect of X. And also, if we were interested in detecting the unique effect of Q, the fact of correlation between the two predictors would have the pragmatic effect of reducing power. We have sort of a counterbalancing kind of situation. Compared with a single predictor, we have less unexplained variance, and that increases power. But on the other hand, we have correlation between the two predictors, and that has the effect of decreasing power. So has power increased or decreased for detecting the effect of X on Y in this situation as compared to the very first situation, that is the bivariate one? Well, it's not easy to know for sure the answer to that question. But I'm going to go ahead and give you a pragmatic answer. The correlation between x and q is quite low. Further, x and y and q and y are both fairly strongly correlated. I mean, these are both strong correlations, so both predictors have good strong correlations with the dependent variable y. So therefore, each of these variables is explaining really considerable variance in y. And on the other hand, the correlation, the overlap between the two predictors is quite modest and small. So it is probably the case that the considerable reduction in the unexplained variance is almost assuredly a stronger effect than is the negative power that comes from the very modest overlap. So in sum, almost assuredly, the power to detect the effect of x is greater here than was the case in the bivariate situation. Now, as I mentioned earlier, it's almost never the case that two predictors are going to be zero correlated with one another, so that in a pragmatic sense, the prior slide demonstrates the best situation in multiple regression. That is, that's a situation when the correlation between two predictors is low. And I really could say, sometimes we're going to have more than two predictors, so I just simply want to say the correlation among the different predictors is low, and further, each of the predictors has a fairly strong correlation to the dependent variable. A combination such as the above maximizes the amount of variance in the dependent variable that is explained, or it very nearly does so, and such a combination also maximizes, or nearly does so, the power to detect the relationship of each predictor to the dependent variable. In other words, if the predictors are highly correlated, if they overlap a lot, to the degree that that is the case, the power to detect the unique effect of each predictor decreases. Now, in some multiple regressions, you may find predictors that are very strongly correlated with one another. And such a situation almost always reduces the power to detect the unique effect of each predictor. So this Venn diagram presents a situation in which two predictors are very strongly correlated. So in this diagram, x and q each explain 25% of the variance in y. Because x and q are highly correlated, much of the variance explained by each overlaps with that explained by the other. So what is the total explained variance? Each predictor explains 25% of the variance in y, but 23% of that variance is jointly explained. So 25% plus 25% minus 23% means that 27% of the variance in y is explained in this situation. So that the explained variance here is considerably smaller than was the case in our Venn diagram, where the predictors were weakly correlated. Recall that there, 45% of the variance was explained, rather than just 27% here. Here, the unexplained variance is 73%, whereas in our example with weakly correlated predictors, the unexplained variance was 55%. So, comparing this slide with the slide where the correlation between x and q was a small one, in this slide we have more unexplained variance. Pragmatically, this means we have more sampling error. So in this situation, the power to detect the effect of x on y is much smaller than is that when the predictors are weakly correlated. I mean, the power is much less for two key reasons. I mean, perhaps the key reason that the power is less is that the two predictors overlap. That is to say, they're highly correlated. And when you get two highly correlated predictors, that markedly reduces the power to detect the unique effect of each one. So that's the key reason why we have less statistical power here. And the secondary reason is that we have greater sampling error. So, I mean, this situation, in other words, a situation where predictors are strongly correlated, is much less ideal than is the situation where the correlation between predictors is weak. I mean, as a general rule, you try to find predictors that have weak correlations with one another, but even so strong correlations with your dependent variable. In particular, that maximizes the variance that you can explain, and that lets you make perhaps the best predictions of the value of y. So in a sense, there's a conundrum created when you have two strongly correlated predictors. When this is so, should you include the second predictor? On the one hand, the answer is no, because it's not going to explain much new variance. It's not going to help you make a much better prediction. On the other hand, your goal might not be per se to explain variance or to make a prediction. You might be particularly interested in the effect of, say, predictor X on predictor Y. If Q is highly correlated with X, including Q doesn't help your power to detect the unique effect of X. It reduces that power. But on the other hand, Q could be a biasing variable. It could be a confounding variable. So leaving Q out could bias the coefficient for X. So in a sense, it's a conundrum. But if your primary goal was to an unbiased look at the effect of X on Y, you might well want to include Q in the equation. So there's no easy answer here, and oftentimes the best thing to do is to run the different regressions, some with the predictor, the second predictor in, and others without it, and to look at both sets of results. Overall, if Q would be a potential confounding variable, you might well want to include it in the regression. So we were looking at Venn diagrams with two predictors in our multiple regression equations, but multiple regression can include 6 or 10 or even many more predictors than this, and somehow the art of multiple regression is perhaps to explain as much variance as you can with a small number of theoretically meaningful predictors. And I'll just mention a pattern that you often see with multiple regression. Oftentimes, the first several predictors in the regression equation really help that equation. Each additional predictor explains considerable new variance. But what can often happen as you get more than 2 or 3 predictors is that you start to reach a point of diminishing returns. That is, as you add new predictors, the variance explained by these new predictors tends to overlap more and more with variance explained by predictors already in the equation. I mean, this thing happens increasingly as you get more and more predictors in the equation. There's more and more predictors, so to speak, to overlap with. So what can happen as you try to stuff more and more predictors to explain more and more variance is that you reach a point of diminishing returns, and in actuality, in a sense, less becomes more. You get something that's more and more difficult to interpret as you keep adding more and more variables in. Before we conclude discussion of multiple regression, I should mention the problem of multicollinearity or collinearity. And you get this problem when two predictors or a combination of more than two predictors are very highly correlated. So in other words, this multicollinearity arises when you get several predictors in a regression equation, and their circles overlap, their variances overlap to a great degree. And in that situation, it's a situation where pragmatically you're going to need to remove one or two of the predictors to get the multiple regression equation to work more effectively. I'll note that statistical packages oftentimes will have a algorithm to toss out a predictor that creates a problem of multicollinearity. So if you have three predictors in the equation and you're wanting to add a fourth one, and this creates a multicollinearity problem, oftentimes the statistical package will simply not let you enter that equation, and it'll give you the results without that predictor in the equation. So in sum, the ideal multiple regression equation is the one where you have predictors that are strongly correlated with the dependent variable and weakly correlated with one another. But sometimes you don't have that perfect situation, so you do indeed deal with the overlapping predictors, and this can reduce your statistical power, and as the overlap gets greater and greater, the addition of these new predictors helps hardly at all or makes things worse, but sometimes these additional predictors may be potentially biasing variables, and so that sometimes you need to go ahead and include them even if some problems emerge. And obviously the great advantage of multiple regression is that the variables that are in the equation are controlled for. And in chapters 10 and 11, we demonstrated controlling for variables using tables, and you saw that the cell counts in the tables got smaller and smaller as more and more variables were controlled for. So that, multiple regression is far more flexible in that regard. It's easy to add in 6 or 10 predictors, and you don't need to worry about cells getting too small. A general rule of thumb in multiple regression is that you should have at least 10 times as many cases as you have predictors. So if you have 50 cases, you shouldn't have, for instance, more than about 5 predictors in the regression equation. The footnote at the end of chapter 23 presents some of the different approaches to multiple regression. And now we're going to move on to some other multivariate procedures. In closing this video, I do want to say that this discussion of advantages and disadvantages of multiple regression in different situations, it's been a pragmatic one. It doesn't cover every possible contingency that one might encounter in multiple regression. And in particular, this discussion has presumed that correlations between variables have been positive. So when you get combinations of negative and positive correlations involving predictors and dependent variables, things can get more complicated than was presented here.